Алекс Mizrahi. Я технический директор компании ChromaWay. Работал с 2012 года на технологии Colored Coins, потом мы перешли на приватные блокчейны. И сегодня я буду рассказывать блокчейн как база данных. Но на английский язык все знают?
Разумеем.
Да, тут очень много терминов, поэтому я думаю лучше на английском. Okay, so I've been involved in blockchain technology for 6 years and did a lot of many things like public blockchains, private blockchains, smart contracts. I did some academic research as well. So I noticed that there are many ways to conceptualize blockchain, to define what it is, its role, its functions, and so on. There is a lot of debate about this. If you do some blockchain project, usually there is always a person who will claim that you're doing it in the wrong way. As an extreme example, some people in the Bitcoin community claim that only Bitcoin blockchain is a true blockchain, and the rest is not blockchain, maybe some kind of database. But I think it's actually a good thing that we have many different interpretations of blockchain, because this allows us to look at blockchain from different angles. It allows us to find an optimal platform for a particular application, or to optimize the blockchain platform for a certain range of applications, to find new users, and so on. In this talk I'm going to focus on blockchain as a database, but I will briefly go through other interpretations so we can see how they all connected. Okay, so Satoshi Nakamoto defined that blockchain is used to prevent double spending in a cryptocurrency, so that total number of coins is conserved in Bitcoin. But in practice, it has many other roles in Bitcoin. In particular, it's used to store the history of transactions. And this is considered undesirable because it doesn't allow Bitcoin to scale. Now there is a new protocol called Lightning Network, which allows Bitcoin users to conduct payments without recording them on the blockchain. In this case, the wallets will be responsible for keeping the history of payments. This will allow Bitcoin to scale, but in other applications, in other blockchain applications, it's actually the point. Storing data on the blockchain is actually the point. One of the first such applications was Namecoin. It allows people to register names on first-come, first-served basis. So somebody who wants to register a name, he publishes a request, and the first person to publish this request receives this name. He can define domain records, just like in DNS system. And anybody who has a copy of Namecoin blockchain will be able to resolve these names. Later, this was generalized into what Peter Todd calls proof of publication. So the idea is that if data is published in an open way, so it can be read by all the parties who are interested in it, then it can prevent a lot of bad stuff like double spending, double registration, double accounting. It can resolve any kind of ambiguity, or it can be used to detect fraud, and so on. So this is very useful when we need privacy, security, transparency, and so on. Now, if you look at it from a different way, in distributed computing, state machine replication is a general method of making fault-tolerant services by replicating servers. State machine is a deterministic algorithm. It receives input data and current state and produces a new state deterministically. A blockchain can be used to replicate the input data, and thus on each machine we will have identical final state. So this can be used for state machine replication, and thus it can be used to make distributed fault-tolerant services. Now there are several sub-interpretations of this. In state machine, state is data which belongs to an application and is managed by state machine. So if this is financial data, it might be called a ledger, like a record of transactions. And then we talk about distributed ledger technology. This is terminology often used by private blockchains such as Hyperledger Fabric. And the machine part of the state machine, it describes the rules of how data evolves over time, what transitions are possible, and so on. And in financial context, it can be called a contract. So this gives a name to a term smart contracts, which is used by Ethereum. There is something common in the three interpretations I mentioned. In proof of publication, data is being published. In distributed ledger, ledger is financial data. And in replicated state machine, state is the data which is managed by this state machine. So in all these cases, we deal with managing structured data. So we are dealing with a database. And this means that blockchain can be described in terms of its functions as a database. So what kind of database it is? Obviously, it's distributed because the data is kept on multiple nodes. But unlike normal distributed databases, it focuses on security rather than performance. It's designed to tolerate not just hardware failures like network failure or server failure, designed to tolerate any kind of failures, including cyber attacks. This is known as the Byzantine fault tolerance. Also, it deals with authorization in an unusual way because usually a server authenticates the users and then it just records its changes. It doesn't record the authorization proof itself. But on blockchain, we record the signature, which acts as authorization proof for each transaction. So authorization can be checked by any kind of a node. So this is also improved security. Thus we can say that blockchain might be described as a secure distributed database. So what does it give us? First, we can use it as a metaphor to explain what blockchain does. For example, Ethereum is often described as a computing platform, but it can be very confusing to new users because why would one pay for a computation which he can trivially do on his own laptop for free? It makes no sense, right? But if you see Ethereum as a kind of a global database, that it may make sense that inserting data into a global database onto thousands of nodes is actually costs some money. And computation is there is just to verify that this data is right, that it prepares this data, and so on. Then we can use this interpretation when we are planning software architecture for a particular application of blockchain. So when you look at code, it might be not clear what code must be in the blockchain level, what code can be in client side, and so on. But if you look at data, you can usually it's easy to understand what kind of data must be global, must be what kind of data you need consensus on. So then you can structure application around this. There are also certain business cases which involve databases. First is consortium database, when you have multiple independent entities who do not trust each other completely, but need some kind of common state, a common database. Blockchain might be a good technical solution because it allows them to get this shared data without compromising on security. So there is no risk that the whole system gets compromised if just one node is compromised, as is with normal databases. And even if you have just one entity, it still might make sense to make a hardened, secure database using blockchain technology. You can, for example, you can run nodes in different branches of one bank, for example. You can also anchor data, anchor blocks into a public blockchain for better security. So by using blockchain data structures, linked timestamping and so on, you can benefit by using, basically you get transparency, security. It will be possible to detect attempts to modify data and so on. And now if you look at blockchain as a database, basically if you want blockchain to be a database, we want certain properties, right? To serve. We want a rich data model which allows us to model a problem domain in a natural way. We want flexible queries to be able to retrieve data, because that might evolve. The way you retrieve data might evolve over the time of application. So we want some flexibility in there. We want fast access to data. So we want indexed access. You want constraints to prevent, if there is an application bug, you don't want it to corrupt your state. So you want additional protection from that. And if in enterprise applications, you might want some integration tools. So you want the blockchain to be interoperable with some existing platforms. And usually blockchains score fairly poorly on this. Like with Bitcoin D, for example, it only gives data about your own wallet. It cannot give you data about the blockchain. It doesn't even give you data about Bitcoin transactions. So if you are making something a bit unusual, you're going to use external software or external APIs for that. And even blockchains which are designed for applications like Ethereum, for example, they often have some troubles that data access is not very convenient, or it might be too slow, so people often try to index the state of the blockchain into a different database, so you have data in two places. That can be problematic. So at ChromaWay, we decided that we can make a project to solve this problem, and we made a project called PostChain. It stores data in relational database, and it actually allows one to implement the logic of blockchain in SQL using SQL schema and storage procedures in pretty much a regular way. Here's how we came to this. So we have been working with Bitcoin blockchain. We made colored coins implementations. And as I mentioned, Bitcoin D doesn't give you data in a good format. So as kind of typical, we took the Bitcoin blocks, parsed them, and put them all in a SQL database, particularly PostgreSQL. And then the mobile clients can sync very fast using the data from this SQL database. They can sync quickly. But Bitcoin itself has many limitations, like total number of transactions, expensive transactions, slow confirmations. So since we deal with privately issued tokens, it makes sense to use a private blockchain, like certain consortium of companies might run their own nodes on a private blockchain. It might be connected to Bitcoin network as well. They will have BFT consensus between their nodes. And since we already keep data in SQL database, it makes sense to use that instead of having it in two places. It makes sense to use SQL as a source of information. So this is what we used. We implemented PostChain. Then we saw an opportunity to generalize it. So it can handle not just like Bitcoin transaction or token transfers, but any kind of blockchain applications. On each node has its own database, and the database is kind of unmodified SQL database software. So basically, PostChain node will connect to its own database. We'll create schema for application. Basically, there are system tables, and there is also application-specific schema, which is described in SQL. So PostChain node implements client API, which is used to submit transactions or to retrieve information from it, connection between nodes, BFT consensus algorithm, which is derived from PBFT. That's a pretty traditional approach for this. And then there is transaction logic, which works with SQL data store. And the transactions can be, so basically on the PostChain side, we parse this transaction, check the signatures, and then usually insert data into SQL database. So only requirement, this can be implemented in procedural language such as Java. The only requirement is that the state of the blockchain must be kept into SQL database, because we rely on SQL's transactional properties to implement consensus, implement security, and so on. So these parts actually customizable, the transaction logic and the schema in the database. And it's possible to define your own like transaction structure, or if you can use our basically a predefined one which supports multiple operations in atomic transaction, multi-signature, and so on. This is an open source project. However, we haven't released it source code of the server yet. It's going to happen in October. Right now there is a client code, and I think next week we are going to release some documentation examples. So if you're interested in SQL databases, here's URL where you can find it. And to conclude, I'd like to note that, as I mentioned, there are many interpretations. So when you're working on new blockchain implementation or new application, it makes sense to look at it from different angles. And particular, that data-centric approach is often, like in my experience, it's very useful. You can see, like, define what data must be public, whether it's okay to data to be published in what format. Maybe you want just commitment. Maybe you don't want to put the total data which belongs to users into a global database, because then there is a privacy issue. Maybe you just want to put a commitment or hash of this data, so it basically gets committed. So basically, yeah, that's it. Thanks for listening.